All right, so video on gravity. Yay. Hopefully short, simple, and sweet. Or sour, if you prefer sour. I don't know. All right, so gravity, you say, I know what that is. Things fall down. That's true, but you got to know why they fall down. And believe it or not, we don't really know why. Like you say, no, we do. Well, not really. We don't really know why gravity, like, we don't know what we don't really understand what it is that makes something literally be pulled down, whether it's things called gravitons or whatever. All right, we're still trying to figure that out in physics. Okay, it's an ongoing problem, but we can model how it acts. Like we can mathematically represent like how much force there is in gravity, or how quickly something will accelerate, how quickly something will begin to move if gravity affects it. Right. So that's what we're talking about here. Fundamentally, gravity is a force, at least at this level. And when you think about it, you're like, yes, things fall down. Well, it's also things that have mass, right? If you want to really think about gravity, it's not things go down, it's things are going towards massive objects. Okay, we live on a planet called Earth. It is a big planet. Okay, it's not the biggest planet, but it's a big planet. It's got a lot of mass, which means we're used to the most massive object near us being the Earth. Okay, which means if I drop something, right, it's going to go down. Where's down? Towards the center of the Earth, towards the center of gravity of this planet called Earth that we live on, which is roughly a sphere. Okay, it's not perfect sphere, but that's okay. It means though that if I was in space and I had this bottle of vitamins and I had this pen, okay, if they are far enough away from a star, far enough away from a planet, etc., somewhere they're far enough away from any other objects, the only appreciable, the only measurable gravity would be between these two objects. And it would be a very, 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 very small amount of force. But over time, assuming these things start with no motion, eventually they will start to accelerate towards each other. And eventually they will form one object, basically. This is incidentally how planets, asteroids, etc., formed, like pieces of dust in space that eventually get pulled together and make bigger and bigger and bigger and bigger objects. And those bigger objects have more gravity, which means they can pull harder, right? You can kind of see the idea here, okay? But we're getting kind of ahead of ourselves, right? I'm just trying to give you that gravity is simply an attractive force between two objects that have mass. Okay, so you keep that in mind and say, okay, got it. All right, you get to higher level physics, it can get more complicated than that, but for right now we say, hey, this is simple, this is high school, we leave it there, okay? We are using this gravity, okay? This is called the law of universal gravitation, okay? Isaac Newton, we can thank him for this. He's got a lot of things we thank him for. He's a pretty good scientist, pretty good mathematician also. But this law, the law of universal gravitation, is doing what? It's telling me if I want to know the force of gravity, right? I have Fg here, the force of gravity is equal to big G. Big G is what's called the gravitational constant. You can see here I have it underlined. It's a constant. It means that number never changes. That number in every gravity equation, when we're using the universal law of universal gravitation, that number is going to pop up. That's 6.67 times 10 to the negative 11. Okay. The unit is very ugly. You're like a Newton meter second per kilogram squared. What is that? Basically, to keep things simple, it is so the other units cancel out nicely, so we're left with newtons, because a force has to be in newtons, okay, or some derivation of newtons, right, kilonewtons, giganewtons, etc. For this equation, it's assuming newtons, okay. So G, if you're confused by this part about the units, just focus on the number, 6.67 times 10 to the negative 11, very small number, okay, has to be in the equation, though. M1, mass of object 1. It does not make a difference which one goes first. M1, M2, you could do M2, M1. It doesn't matter. A times B is B times A. Okay, so we don't care what our first object is and our second object. We just care that they both get put in the equation. Okay, so I have the mass of the first times the mass of the second. Got to be in kilograms. Has to be. If you have grams, you'd have to convert that to kilograms. Otherwise, this will not work. Okay, and if you're confused by that, if you're like, well, wait, why? They're both mass. It would be like me saying, like, how far is it from New York to LA? And I say, I don't know what would be an equivalent. If I said, 16 trillion inches, you'd be like, okay, that's a weird unit, right? It would have to be converted right back to miles for it to make kind of sense to us. Okay, but imagine if I just said 16 trillion miles, you'd be like, wait, no, that's not right. Right? That's not how many miles it is. So I don't know. I don't know if that analogy makes sense, but the logic is you have to use the right units. If it's expecting kilograms and you plug in grams, it's going to be off by 1,000 because there's 1,000 grams in a kilogram. Okay, so just keep that in mind. Very important. So 2 objects in the numerator, and then we're dividing by the radius between the objects. Now, technically, it's a radius because you're going from the center of the object to the center of the other object. Okay, usually, at least for high school level, we're kind of making the assumption that the distance from the center of the object to the edge is so small compared to the distance between the objects. We're talking about space usually, right? So these are very large distances. Usually, the neglecting the center to the edge, it's not enough difference to really matter. Okay. Now, if you're taking a physics class, if you're taking higher level stuff, then you might want to consider it. But I'm just trying to say that, for high school level, I would say the main thing is the distance between the objects. Okay? You want to be technical, you do need to find from the center to the edge plus the distance. But again, usually on scales of space, cosmic scales, usually not significant enough to matter. Okay? Got to be in meters, though. Has to be in meters. If it's in kilometers, it ain't going to work. If it's in light years, it ain't going to work. You have to convert to meters. Okay, that's also very important. All right. So let's say I have a sample problem. Okay, so I could have find the amount of gravitational force between Earth and the Moon. Right, 2 objects we know, and I give you the distance between them. Okay, which is incidentally the average distance, but that's another thing, of 384 million meters. Okay, so what I would do is list out my variables. Do I have M1? Do I have M2? Do I have the radius? G, of course, never changes. And then you say, oh, I'm trying to find FG. Okay, you take those numbers, you plug them into your equation. Notice I wrote it like this. G out here, you could put it in the numerator. Nothing wrong with that. It's the same exact thing mathematically. Okay, so if you want to write G up top, you can. Just don't put it in the bottom, please. That would be a problem. Okay, so we do this. Don't forget to square the radius. Okay, this is where parentheses can be really, really nice, because if you just square 10 to the 8th, it ain't going to work. You got to square the whole thing. All right. I do these calculations. I say equals, and my calculator spits out, in this case, I rounded it to the hundreds place, 1.99 times 10 to the 20th newtons, which is a pretty big number. That's a lot of newtons. Okay. The amount of force between the Earth and the Moon, is what keeps the Moon from flying off. Okay, and for those who know a little bit about astronomy, the Moon is eventually, we think, going to escape Earth's gravity. Okay, it's going around the Earth fast enough where its orbit is getting bigger every year. Okay, but if there was no force of gravity, it would just fly off. Imagine spinning a ball above your head, like on a string. The string rips or the string breaks, the ball flies off. Right, it would be like that. Gravity would be like that tether between the two, keeping them somewhat close. Okay, force of gravity, incidentally, from the Moon is what causes the tides on the Earth, right? The oceans of the Earth have a lot of mass, and they're being pulled every day towards the Moon. And because the Moon is going around the Earth, and because the Earth is rotating, right, you can have twice a day, you can have tides occurring in the oceans, which moves water closer inland or pulls it out more towards sea. Okay, so the tides are caused by this gravity between the Earth and the Moon. Okay, got more examples, right? You could take these answers, right? I have a follow-up question. Applying Newton's second law, could you find how much acceleration there is? This is kind of, we're getting away from the main crux of the video. But again, to show you that forces, right, you can figure things out with these forces, like how much acceleration is there, how quickly things are going to move. That's why we do this stuff. We don't just do force calculations just to have a number, right? We want things we can measure, figure out, and make predictions with it. All right, but that's our short video on gravity. The name of the game is practice. Okay, you want to do as many practice problems as you can with this kind of stuff, both knowing where to put the numbers, making sure they're the right units, and then making sure you put it in your calculator correctly. Okay, important stuff. So hopefully this helps, and hopefully you say, great, I get the basics of gravity. Have a great day.